Welcome to Maths with EJD. In this video, we continue with different ideas on numerical optimization techniques. And we've started the first part talking about gradient-based methods, gradient-based methods for numerical optimization. So previously we had considered gradient descent, where you go in the opposite direction of uh, of a slope to find the minimum of a particular function. Then after that, we have the Newton's method, which will be the our focus in this video. Afterwards, we'll be talking about the conjugate gradient method, which seeks to make solutions convert faster based on an improvement on the gradient descent method. So previously we've considered this. Now our focus goes to the Newton's method, which has a bit of resemblance with um, Newton-Raphson method for root finding. Okay, now let's go to see what this whole Newton's method is about. So Newton's method. Okay, what's the concept of Newton's method? Newton's method is an optimization algorithm. Is an optimization algorithm that algorithm algorithm that improves upon gradient descent by considering both the first and second derivatives. I mean, these are the gradients, right? These are the gradients. The first derivative is the gradient, and the second derivative is the Hessian of the function to find its minimum. Okay. Now the Newton's method uses this information, that is the gradient and the Hessian. It uses this information to make more informed updates, more informed updates to the solution, allowing it to converge faster than gradient descent in many cases. However, it requires computing the Hessian matrix, computing the Hessian matrix, which can be computationally expensive, which can be computationally expensive, particularly for high dimensional problems. Okay, I mean, in numerical analysis, we always have to reach a compromise between accuracy and computational expense, for sure. Okay, so let's look at the formula for this. So update rule, the update rule in Newton's method, in Newton's method is xk plus 1 equals xk minus h x of k, I mean h of xk inverse multiplied by the um first derivative of f of x of k. So now we have something additional, right? So in the case of gradient descent, we had the learning rate multiplied by the derivative or what is called the gradient, right? But here, in addition to the gradient, we also have the inverse of the Hessian together with that. So this is the update rule. But then let's know which each of the components. So first of all, xk is the current estimate, is the current estimate of the minimum. Then we have grad of f of xk, which is the gradient. This is the gradient of first derivatives of the function at xk. Then we have h of xk, which is the Hessian matrix. The Hessian matrix. Talking about second derivatives now of the function at x sub k. So let's look at the process involved. Um, process. So the first thing to do is to compute. So compute the gradient. Compute the gradient. Of course, you see the gradient is grad f of xk. So that's the first step. So the gradient is a vector of first order partial derivatives that points in the direction of the steepest ascent. You know, that's not descent now, like steepest ascent. For minimization, we need to move in the opposite direction. So steepest ascent goes up, but if you are minimizing, we go in the opposite direction, like for gradient descent. So we compute the gradient. Then number two, we compute the Hessian matrix. The Hessian matrix, that is our h of x of k, or h of x in general. Okay. Three, we update the solution. Update. I mean, for step two, before I go to step three, for two, compute the Hessian matrix, right? The Hessian is a square matrix of second order partial derivatives, which describes the curvature of the function. It indicates how the gradient changes as you move in different directions, providing information about the shape of the function. Okay, so the Hessian is a square matrix of second order partial derivatives, which describes the curvature of the function. It indicates how the gradient changes as you move in different directions, providing information about the shape of the function. And the third step is update the solution. Update the solution. Of course, you have the update rule, so just keep going on. So, and that is to say, The the update step uses the inverse of the Hessian matrix to scale the gradient, adjusting for curvature. So this typically leads to faster convergence compared to the gradient descent, especially when the function is well approximated by a quadratic near the minimum. Okay, so those are the steps involved. So let's take an example and see how that goes. Example. So let's consider a simple quadratic function that is f of x comma y equals x squared plus 2y squared minus x squared plus 2y squared minus 4x minus 8y. Okay, so in that case, right, we go for the first step. We have step one, which talks about gradient calculation. We have the gradient calculation. That's simply first derivative, right? So grad of we have grad f of x comma y. So that means we have a collection of partial f, partial x, and partial f, partial y. So that simply means that so we differentiate this function with respect to x. That's the first part. So here you have differentiate with respect to x. That's 2x, no x here, that would be 0. So you have 2x minus 4, for that part, 2x minus 4. So this is 2x minus 4. Then differentiate the same expression for y. So no y here, that's 0. There's y here, so we have 4y. And here, this is 0, and we have 8. So we have 4y minus 8. That's the second grad. Differentiating with respect to y, that is 4y minus 8. So that is the grad, basically. So that's the gradient calculation. And then that takes us to step 2. So step 2. So for step 2, we have the Hessian calculation. Hessian calculation. So for the Hessian calculation, we have h to be equal to h of xy rather. H of xy is equal to partial squared f partial x squared, then partial squared f partial x partial y. I mean, you can look at it like this is x, y, and this is x, y. Okay, so x, that's you have partial x squared. Then here you have x, y, so partial squared f partial x partial y. Then when you come down here, you have partial squared f. That's second derivative, right? Then it will now be partial. So you can say partial y, partial x. It doesn't matter which one comes first because this and this will automatically be the same no matter the order. Then lastly, you have partial squared f, partial y squared. So differentiate with respect to y twice. Okay. So now we have f and we've already got partial f, partial y. So you see we have partial f, partial x. Okay, let me just what do I do? Let me use this. Let me just say, this is partial f, partial x. We know that this is partial f, partial y. So partial f, partial x squared means we differentiate this one again. We differentiate this expression with respect to x. That's differentiate 2x. Okay, well, I mean, to make it better, let me just take the pain to write it out again. So we have partial f, partial x to be equal to 2x minus 4, and then partial f partial y is 4y minus 8. So with that in place now, so we can proceed. So we have h of x comma y to be equal to, so the first one is partial squared f partial x squared. That means differentiate this one with respect to x, and that is simply 2, right? So we have 2 for that. Then the next one, partial squared f partial x partial y. So this same one, differentiate with respect to y. Since there's no y there, that would just be 0, right? And then for the next one, which is this partial squared f, partial y, partial x. So that's partial squared f, partial y, partial x. So you have partial f, partial y, differentiate with respect to y, and that will simply give us, um, I mean, that will give us with respect to x rather, because it's already partial squared f partial f partial y, that's partial squared f partial y partial x. So since there's no x here, that will just be 0 also. Of course, we already know that the numbers in this corner will be, the values in the corner will be the same. And lastly, we have partial squared f partial y squared. So this function, this expression now, we differentiate with respect to y, and that gives us 4. So the Hessian matrix is 2004, basically. So that goes. So this is what we need here for the Hessian, just like we got this um for the gradient. Okay. Now we have the gradient and the Hessian. So the next thing we want to do is to apply Newton's method. So step 3, apply Newton's method. Okay. So suppose, since we have two variables, so we need initial guess for the two. Suppose we have, suppose we start with an initial guess, x naught equals 1, comma 1. That means x is 1, y is also 1. Suppose we start with this. So the first step is to compute the gradient and Hessian at this point, this given initial guess at this point. So it means we have the grad of f1, comma 1. So that means that, we have those grads, right? So the grad f grad x is 2x minus 4. So when x is 1, so we have 2x minus 4 in short. So that means for that part, we have 2 into 1 minus 4. Then the other one is 4y minus 8. That's 4 into 1 minus 8. So all of that will just be 2 minus 4, that's minus 2. 4 minus 8, that's minus 4. So that is grad f at 1, 1. Then we now have we have h at 1, 1. Of course, the Hessian matrix has no variable anymore, so it's just what it is. So we have 2004, so we can just write it down that way. So this is simply 2004. So there's no x or y to substitute 1 into, so that is taken care of. So the next thing we want to do is we now apply the update rule. So now apply the update rule. Apply the update rule. So that means that x1 would be x naught minus the Hessian evaluated at x naught. That's inverse of that, because normally it should be grad over Hessian. So then del f evaluated at x naught. So if we do that, of course we have to first compute the Hessian and all that. So h evaluated at x naught. Of course, we know that doesn't change. That simply means we are looking for the inverse of 2004. We are looking for the inverse of 2004. So the inverse of this. And because of the nature of this matrix, the inverse would simply be for a diagonal matrix like this, the inverse would just be the inverse of the diagonal elements. So we don't have to stress ourselves too much. If you use the standard procedure, you still get it. So we have 1 over 2, 0, 0, 1 over 4. So the inverse of a diagonal matrix would be a matrix with the inverse of the diagonal elements in the diagonal still. Like that's the principal diagonal. So that goes. So we have the inverse right there. So we have got this now. So the next thing we are going for the whole of this. So now we have h of x naught grad f of x naught. So that means we have half 0, 0, 1 over 4 multiplied by f of x naught, which is simply minus 2 minus 4. And then, of course, I explained to you the easy way of doing this. So this is one column. So you just write it once, okay? Minus 2 minus 4. Oh, you write it, you are going to have one column, right? So then this is two rows. So it means you are going to write this twice rather. So you have minus 2 minus 4, write twice. Then over superimpose this half 0 here. That's half 0. And then when you come here, there's 0, 1 over 4. So this is 0, 1 over 4. So, and that's what we have. So we have this now. So this is that. And with this now, we just simply have minus 2 times half. Minus 2 times half is minus 1. Then minus 4 times 0, that's, we have plus 0 right there. Minus 2 times 0 is 0. Then minus 4 times 1 over 4, that's minus 1, I think. Yeah, it's minus 1. So that means that so this is minus 1 easily. So it means that the hx naught, oh, it should be the inverse, sorry. So it should be the inverse of this. Apologies. So that means that hx naught inverse multiplied by the grad of f of x naught is equal to minus 1 minus 1. So we have that. So we can then have the update. So we can say, therefore, the update is x1 equals x naught already. We know x naught, our x naught here. Of course, we have to take this like transpose, so we can have it this way now. So this is 1. So this is 1 comma 1. Oh, this is 1 1 in short, minus. So general, the formula, don't forget, is x naught minus hx naught inverse. Okay, grad f of x naught, so that this is now 1 1 into minus 1 minus 1. So that means that x1 would simply be 1 minus 1 plus 1, 1 plus 1 in short. So that is simply 2 2. So that's the update. And actually, I think that should be the optimal solution, because this is a very simple problem. It's a simple one. But then, of course, if you're not, if you don't know the stopping criteria, if you need to do further iterations, all you just need to do is now just go and let's talk about, this is step 3 so far. So step 4 now. So in case this is not the final result, so in step 4 now we have next iteration. So you keep iterating until you have your stopping criteria. And just like I said in the previous video, stopping criteria can be number of iterations. So you can just be told to do 4 iterations or 3 iterations or a number of iterations. So once you do number of iterations, you stop. Then the other criteria could be convergence to a particular value you already have been told. So so you would repeat this process. You would repeat this process, recalculating. Now, just like this method is very fast because we use both the grad and the Hessian, both the gradient and the Hessian. So it converges very fast, just like we discovered for root finding for Newton-Raphson. So it's about the same concept. So we repeat this process, recalculating, recalculating, recalculating the gradient and Hessian at each new point, xk. In fact, you can see just on one iteration, we've got the result right there because it's 2 2 most likely. So Hessian at each new point xk until until convergence. Until convergence. Okay. So given that this is a quadratic function, given that this is a quadratic function, Newton's method would converge very quickly, would converge to the minimum very quickly. Okay. I mean, just like I guessed, that first iteration has probably taken us to the convergence. But let's see the Python code, which helps to solidify things like this. So imagine the Newton's method that we have displayed right here. Of course, we define the function x squared plus 2y squared minus 4x minus 4y, that like this. And then we have the grad, the f dx is 2x minus 8, the f dy is 4y minus 8, and all that. So we are returning these values for this. You have to evaluate them at this function is defined to supply x and y, just like the one we had for initial guess. So, and then we have the Hessian matrix, which we have also supplied because the squared f dx dy is the same as the squared f dy dx. So we just have 0 for that. So we have 0 for x squared and y squared. That's the squared f dx squared, the squared y, the f dy squared. And then, so we define the Newton method. This is where the whole Newton method is going. So we have a tolerance of 1 raised by minus 6, and we want 100 iterations. We may not need up to that because the problem is quadratic. If it was cubic or quartic or something, maybe you have a bit more, it will take a bit more effort to converge. Then here for I in range of up to maximum iteration, we have the gradient, we have the Hessian, we compute the inverse of the Hessian. Thankfully, in that Hessian we got, it was a diagonal matrix. So the inverse will simply be the inverse of the diagonal element. It will be a matrix containing the inverse of the diagonal elements of the initial matrix, and that will be the inverse of this Hessian matrix. Then you check for convergence. So here we are checking for convergence by comparing. So normally to check for convergence, you would have checked the difference between the current result and the previous one you got. So now, of course, if you check x1 and x naught, it's like 2 minus 1, 2 minus 1. So you still have 1, which is absolute of 1 is bigger than 0. It's still bigger than 0. So I'm sure with one more iteration, we should get where we need to get to. So we also want to get maximum iterations reached. The initial guess is 1, 1. So you can change the initial guess to whatever you like. So if I run this now, you see it converges after 2 iterations, and the optimal solution is 2, 2. So and the reason for 2 iterations is because if you check the 1, 1 that is x naught and the 2, 2 that is x1, there's still a distance of 1 between them. I want to believe. So we need to do one more. So if our initial guess was 2, 2 already, we would probably just need one iteration. Yeah. So you see, one iteration, we get the answer if the initial guess is 2, 2, because it's more like you have guessed right. Okay. So what if I do it like 1.5, 1.5? I believe that should also take like one iteration, hopefully. So, okay, it still takes 2 iterations. What if I go to 1.6 each? If I go to 1.6, 1.6, so the closer it gets to 2, the less the iteration will be. Okay, 1.6 is also giving that. So let me see 1.8 each. Let's see if it still requires okay, still 2 iterations. What about 1.9? I'm just pushing it. 1.9 still takes 2 iterations until you get the actual 2 itself, right? So you have 2, 2, and then you just have the whole thing in one iteration. So if you check for convergence from what we did initially, since we started with 1, 1, we need to do one more iteration to get the right results. But of course, just continue the process again. Just substitute 2, 2 into the next one, and you get the next value. Okay, now that we know that it requires 2 iterations, let me see. Okay, then we're back here. Okay, so the next step of iterations, right? So next we just need interestingly, this is pretty easy. So now we have let me just go for second iteration. I feel lucky. Oh, how do they say it now? The second iteration. So we now need x2, which is equal to x1 minus the Hessian of x1, the inverse of that, multiplied by the grad of f of x1. Okay. Yeah, so with that, we have x1. We know our x1 is 2, 2. Then we need this whole part now. So first of all, the grad of f evaluated at 2, 2 would simply be all these things. This is 2x minus 4, 4x, 4y minus 8. If you remember, this is 2x minus 4, 2x minus 4, 4y minus 8. So we have, okay, this will be 2x, that's 2, 2 minus 4, then comma 4, 2 minus 8. So all that takes us to 4 minus 4, 8 minus 8, that is 0, 0. So that is the grad right there. And of course, we still have our, so that's the grad, it's 0, 0, basically. And then how did we use the grad at this other point? So the grad we got at first was minus 2, 4. So we are going to need that later, right? And interestingly, our Hessian is already fixed. So Hessian at 2, 2 remains the same. It's 2, 0, 0, 4 again. So now we need Hessian at x, Hessian at x1, right? The inverse of that for sure. So, and of course, it's the same matrix. So it's 2, 0, 0, 4 inverse, and that is 1 over 2, 0, 0, 1 over 4, basically. So still the same. So if these values still have like 2y and 2x, substituting 2, 2 into them would probably have changed the values. So this should have like be like Hessian evaluated at 2, comma 2. So now we can get the Hessian evaluated at x1, the inverse of that, multiplied by the grad of f of x1, that is half 0, 0, 1 over 4 into, what would that be now? It's 0, 0, I think. Yeah, it's 0, 0. So 0, 0. Okay. So of course, this will just simply be, so it means you just have 0, 0 twice, and then you have half 0, then 0, 1 over 4, and all of that is just simply going to be 0, 0. So with this now, we go for the next iteration. So we say therefore x2 is equal to x1, which is 2, 2, minus h of x1 inverse multiplied by grad of f of x1. That would be 0, 0. So once you get the same answer repeatedly, so you see, second iteration is giving the first result. So you see, there's no difference between where you're coming from. So you can just say and conclude that since 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 x1 is exactly equal to x2, that is the absolute value of x2 minus x1 is equal to 0, which is, it's equal to 0, right? That simply means that the solution has converged, the result has converged, because this is supposed to be less than 1 or something, or less than the tolerance limit. So this is far less than, if our tolerance limit was, say, 0 point or 10 raised per minus 6, right? 10 raised per minus 6, which is still a small number, but then this is absolutely 0. So, since x1 is equal to x2, the solution has converged. The solution has converged, and the minimum solution, the minimum value of x is x equals 2, 2. So those are the minimum values, meaning that x is equal to 2 and y is also equal to 2. So if you need the minimum of the function itself, you just substitute this 2, 2 into the original expression and you're good to go. But then we can actually stop here. So normally, if you want the minimum value of the original function you were given, that this x squared plus 2y squared minus 4x minus 8y. So you just substitute directly. So you can have minimum. Let me just do this. So minimum is actually minimum f of xy, so to speak. Minimum of f of xy is the same thing as f of 2, comma 2. So when you put 2, so you have, this is 4, this is 8, 4 plus 8 is 12. Then here you have what? Minus 8. This is minus 16, I believe. So this is 4 plus 8, 12. 12 minus 8 is minus 4. Minus 4 minus this. So the minimum value of the expression itself is minus 20. If you're interested in that, you can actually do that. Okay. So that means that the minimum value of x and y will be 2, 2, while the minimum value of the function itself is actually minus 20. Okay. Is it minus 20? Have I made a mistake? I think it should be 4 plus 8, 12. 12 minus 8 is 4. Oh, yeah. 4 minus 16 is minus 12. Sorry, it's minus 12. Thank, thank God I got that. Minus 12. Because, 8 cancels 8. So 4 minus 16 is minus 12 easily. So the minimum value of the variables x and y are 2, 2, while the function itself evaluated at this point will be minus 2. So, I mean, we can also graph this to see how that works. So, like that. So, I mean, this has been a nice experience. Let me see if we can get some practice questions before this is ended. So let's see some practice questions in this light. This is interesting. Practice questions. All right, so let's see. Practice questions. Okay. Um, for for f of x, comma y equals x squared plus y squared plus 2xy minus 4x minus 6y. For f of x, comma y equals x squared plus y squared plus 2xy minus 4x minus 6y. Okay. Compute one iteration. Compute one iteration of Newton's method from x naught y naught equals 0, 0. That's like the initial guess. Then I have this one that is interesting again. That's question 1 here. Question 2, solve okay. I think I'd rather just let this slide because it's looking like root finding that we had done previously. So I would rather keep it at matrix level. So find the minimum, the minimum, then to write many things, minimum of f of x, comma y equals x squared plus 3y squared minus 4x minus 6y using Newton's method. Okay, start at 1, comma 1. Okay, now let me see your answer to these problems, to these practice questions in the comment, either on YouTube or on Facebook. Of course, don't also forget to modify the Python code to solve this problem. You can get the Python code only on Facebook. I'm not able to put it on YouTube. So let me see this in your comment. In your comments also, let me see how helpful these videos are. You can let me know how helpful these videos are. Also, let me know if there's a topic you'd like me to teach you, a problem you'd like me to solve. If you have subscribed, thank you so much for that. If you have not, go ahead and do that because there's so much more coming your way. Then, of course, hit the notification bell so you can always get alerted each time a new video is released. Then, like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.